working. This section's gonna also require a lot of calculator. So I like Decimos.com for my calculator. If you go to Decimos.com, looks like this, and you can just click on graphing calculator. I'm not gonna be using the graphing aspects, but it's a good calculator anyway, or you could use your own if you have a scientific calculator. I actually don't love the iPhone calculator. So I wouldn't recommend that, but if you know how to use it well, then that's fine. All right. So let's get started here on this section. This section is actually going to involve, I think it's 5 formulas. All right. 5 formulas. Now, formulas can be intimidating, but I think what's the hardest part about formulas is having to memorize them. All right. Do we have to memorize formulas for this class? No. We're allowed to use our notes on the test, right? So let's not be too scared of them. I'm not asking you to memorize any of these formulas. You just have to know how to use them, okay? So we're going to get 1 practice of each formula here in the notes, and then we'll get a puzzle piece today/tomorrow where you practice each of them 1 more time, okay? Okay, so first one here, exponential growth formula. So this one says y equals a parentheses 1 plus r, close the parentheses, to the power of t, all right? So let's define all these variables. This is going to be very important for you to have on your notes. You can reference it. So a is the initial value or the initial amount. Oh, okay. A is the initial amount. Just 1 second here. So yeah, Litzy said the notes aren't attached. That is correct. So for the notes, you got to go back to the top of the unit, and that's all the notes together. You're very welcome. All right. Okay, so A is the initial amount. All right. R is the growth rate. But very important here, make sure you have this. We have to write that as a decimal. So I'll show you how to do that. T is time. Y is the final amount. So I would say that A and Y are kind of connected here. A is what you start with, Y is what you finish with, okay? The scale factor is probably the least important here. Let's go ahead and write it down. So the scale factor is 1 plus R. We said on our last section of notes that the base of the exponent was the multiplier. And so in this case, the base of the exponent is 1 plus R, okay? It's that whole parentheses is holding up the exponent. So that's gonna be our scale factor. Once again, I think that you knowing the scale factor here is probably the least important thing. It's very important that you know these first 4 definitions. If you know the scale factor, great. If not, don't stress, okay? Okay, so here we go. Your grandmother put $2,000 into an account when you were born. Now that to me sounds like the initial amount, right? We're starting off with $2,000 at birth. It has been earning interest at a rate of 3% per year. So R is going to be 3%, but we can't put it at 3%, okay? Because we have to put it as a decimal. So to convert that to a decimal, we have to move the decimal place twice, or you can divide it by 100. The word percent literally mean per means divide in math, and cent means 100. Like a century is 100 years. You know what I'm saying? So this is actually 3 divided by 100, which is 0.03. So that's what we're going to be using for our R is 0.03. So that's usually, I'm going to say always. It's always given to you as a percentage, and then you convert it to a decimal by dividing it by 100, okay? All right, what else do we need? Time, right? So they said time, 18 years when you go to college, right? And then Y is what we want to know. So we know in math that the thing that we want to know, we leave that as a variable, correct? And then everything else we should fill out with numbers. So I'm just going to follow along with this formula. I'm going to write down, I'm just going to fill in all the numbers there except for Y. So I'm going to get Y equals 2,000 parentheses 1 plus 0.03 to the power of 18. So no crazy math there, right? All I did was just plug everything in. From there, we are definitely going to use a calculator, okay? We don't need to do anything else. We're just going to type this into the calculator. Even me, Mr. Barry, literally a math genius, I cannot do this without using a calculator, okay? So don't try to be a hero here. So I'm just going to remember what I have there. I'm going to go over to my calculator, my Desmos. So I'm going to do 2,000 parentheses 1 plus 0.03 and close the parentheses. That looks good so far, correct? Now we need an exponent of 18, right? So for exponent of 18 on Desmos, you can pull this up and you can press this A to the power of B button. But since we're in this unit, it's probably a good thing for you guys to know there's a good shortcut on computers for exponent, and it is Shift 6. If you hold Shift and press 6, it looks like a little up arrow, and that means create an exponent for me if we're talking math. And so that creates an exponent. Now I can type in 18. So my calculator gives me that. We'll round it to the second decimal, so we'll round it right there. But you have to look at the one after that, correct? So since the one after that is another 6, I round that one up to a 7. So I have 3404.87. Y equals 3404.87. And yeah, with money, we always round to the second decimal place. Does that make sense? Get it? Sense? Awesome. It's pretty good, right? You can make an extra $1,400 for keeping your money in the bank. Do you guys know that if you put your money in the bank, it depends on if it's a checking account, no, but if you put it in a savings account, they actually pay you money for having your money sit in there. It's not going to be a lot of money unless, yeah, if you wait for 18 years, it will be a lot of money, but you get a little bit every year, but it does add up. Okay, now we're going to switch over to a little bit different here. This is called exponential decay. Now I'm going to say that this one looks the exact same as it did before, right? With one difference. In that parentheses, the plus turned into a minus, right? So this is when something is decreasing in value. So the previous one, our money was increasing in value. This one, it is decreasing in value. So A is still the initial. The initial is another word for a starting amount. Para empezar, if you will. Now, R here is the decay rate. So instead of the growth rate, it's the decay rate. Now, this is usually going to be given to you as a percentage as well, so we'll still have to convert that to a decimal. T is time. Y is the final amount. And the scale factor is going to be the base of the exponent, which will be 1 minus r. Okay, your dad buys a dream car for $25,000. It depreciates at a rate of 9% per year. So if we do 9 divided by 100, that's going to be 0.09. Most things you buy, like cars, do depreciate in value over time, right? They're worth less next year than they are this year. There's one big exception to that. Does anybody know anything that increases in value while you use it? No. Increases in value while you use it. I'd say there's only one thing in the world. It is a house, I would, or apartment. If you own that, then you use it, but house prices and apartment prices all kind of always go up. They like, sometimes they do a little dip, but then they keep going up because, especially in Orange County, like Orange County's not getting any bigger, right? But everyone wants to live here, so the home prices always go up. All right, what else do we need? T time is 5 years, and Y is what we want to know. So we'll say Y equals $25,000 times 1 minus 0.09 to the power of 5. Okay, so we're ready to type that in the calculator. All right. So what was that one? 5,000, right? And 1 minus. So what I like about Desmos too is you can just go in and edit your old one. Oh, it's 25,000. Thank you, Ben. Easy fix. So 25,000 times 1 minus 0.09 to the power of 5, and we get 15,680 cents. Since we're rounding to this spot, we look and it's a 3 after that, so we're going to round that, keep it down to 0, right? So 15,600.80. Cool. All right. Next one is compound interest formula. So this one's always having to do with money. So it's a little bit more complicated than the one we were doing earlier. So let's go through it. P is actually still the initial amount. R is the interest rate. And you guessed it, it's going to be a decimal. n is kind of our new thing here. This is number of times compounded per year. Number of times compounded per year. Now, what the heck does that mean? Well, let's build a little box down here. So all of these are going to say some compounded something, compounded. So there will be a couple of options. One option, annually. So if you do something annually, how many times per year do you do it? If you do something annually, that means you only do it one time per year. So your n would be 1. If you do it semi-annually, how many times do you do it per year? 2. You're supposed to go to the dentist semi-annually, twice a year. If you do something quarterly, how often do you do it? 4 times per year. If you do something monthly, how many times do you do it per year? 12. And if you do something daily, how many times do you do that per year? 365. So I think those are the only ones you'll see there. You could do a weekly one. I think there's 52 weeks in a year. I don't see that very often, so I wouldn't worry about it. Technically, you could do it hourly. And what would that be? 365 times 24, whatever that is. I rarely see that either, so I'm not going to write it down. That's good. It's going to be one of those. Okay, so T is still time. Y is the final amount. And the scale factor is going to be 1 plus R over N. Remember that scale factor is kind of whatever's holding up that exponent. So in all of these so far, we've seen that it's a parentheses that's holding up the exponent. Okay, so now let's do our problem here. So you invest $2,000 when you're born. So that's my initial amount, 2,000. We got 3% interest. So R is 3%, which we know we need to convert. 3 over 100, 0.03. It cannot be 0.3. 0.3 is actually 30%. 0.03 is 3%. It says compounded monthly. So that would mean that N is 12. And then we have our time here is 18 years. All right, so we'll set it up here. Y equals 2,000 parentheses 1 plus 0.03 over 12 to the power of 12 times 18. Now, anytime you have multiplying in the exponent, on some calculators, you need to use a parentheses for that. So I just always use a parentheses. for the 12 times 18 up there. Probably a good habit to be in. On Desmos, you actually don't need it, but on some calculators you do. So I would just make that a habit, okay? All right, so now we just need to type that into a calculator and see what we get. All right, so I got 2,001 plus 0.03 divided by 12 to the power of 12 times 18. Does that look like how I wrote it? I would say yes. So we got 3429.70. Was it 80? No, it's 70. I might have said 80, but all right, cool. Two more formulas here. Doubling time and half-life, okay? So these two are actually, they're different than the other three, but I'd say these two are related to each other. If you look at them, they're kind of similar. This one has a base of 2, which is like doubling is multiplied by 2, right? So that makes sense. This one is has a half there, which makes sense because it's half-life, right? Okay, so let's define our variables here. So for this one, n sub 0, that's all one variable. N sub 0, we call that, okay? And that is initial amount. Man, that first thing keeps being initial amount, all right? T is time. All right. D is doubling time. So it's how long it takes to double. And then the n out front is the final amount. Our scale factor here. Any guesses as to what's our scale factor? What's the base of the exponent? 2. Just the base, right? The base is 2. The base is the thing that's holding up the exponent. All right. So talking about COVID here in this problem, which actually these exponential functions are used to describe phenomena like COVID when it was first started spreading. It was using a formula just like this. It's kind of changed since then because now it's going down. Now it's actually turning more into this one. But yeah, at the beginning it was like this. So the data shows that at one point it doubled every 20 days, okay? Doubled every 20 days. That is my doubling time, okay? So D equals 20. How long does it take to double? The problem will tell you. N sub 0 is the initial amount here, and it tells us we started off with 4. And then it's asking about 400 days, right? T over D. So I got 4 times 2 to the power of 400 over 20. All right, so I'm going to type that into a calculator. Remember, I'm going to do my shift 6 for my exponent. 400 divided by 20. Oh boy. 419,000, or no, that's more than that. 4,4194,304. 4194,304. So over 4 million infections after just 400 days. Yep. So if it seemed, yeah, so like I said, if it seemed like, we were thinking back to last March, it was like only a few people in the country had COVID and then it really blew up. This is really why, because this is how viruses work, is they double like this. Yeah. What we try to do with masks and stuff is increase the doubling time, right? So if we can increase the doubling time to like 1,000 days, and it takes a long time for that to double. So then less people would be infected. That was the goal. All right, so now let's switch over to our last formula here, which is half-life. Okay, so a lot of this stuff is going to be the same. N sub 0, actually, this is going to be the exact same as the previous. So N sub 0 is initial. Okay, T is time. Oh, the only difference is H is half-life. Technically, you could call that half time because we called the other one doubling time, but they usually call that half-life. I guess they don't want you to get confused with halftime, like a football game or a soccer game or whatever, basketball game. And then N is final amount. And then our scale factor here is going to be 1/2. Okay, so half-life is very often seen in what's called radioactive substances. I'm not a chemistry teacher for sure, but I know enough about chemistry to know that there are some elements that actually decay over time. They lose mass. I don't know where it goes. So I don't know that much, like I said, but I know that they lose mass. Okay, so this this particular one, it says it has a half-life of 84 days. So that is going to be our H is half-life. It says we're starting off with 100 grams. And then it's asking about how much we'll have in 300 days. So we'll do 100 times 1/2 to the power of 300 over 84. What was it? 300 over 84? All right, so that 100 grams, now it's turned into 8.4 grams. Oh, that did take us the whole period. All right, that's okay. That was good stuff.